Hello, everyone. My name is Macarena Garcia Marin. And first of all, I wanted to thank you all for joining me today to talk about the James Webb Space Telescope and the incredible science that it's delivering. I also wanted to thank the organizers for giving me the opportunity to be here with you today. So let's get started. Let me begin by saying that JWST, it's an absolutely fantastic telescope that has surpassed our expectations. The images are twice as sharp, the optics are more stable than expected, and the instruments are more sensitive than we thought they would be pre-launch. We have fuel for about more than 20 years, and the telescope is now on its third year of mission. It is truly, the bottom line is that JWST is truly fulfilling its promise of revolutionizing astronomy. So let's talk a little bit about the light. Telescopes are machines to collect light, and astronomers will use that information from the light to try and understand all the astronomical objects and the universe around us. This diagram shows an image of Isaac Newton at the time where he used a prism to filter the sunlight and disperse it in its colors. And because it is in the visible, we see blues and reds and yellows, etc. So this is a visible rainbow. But of course, we know that the light is not just the visible. The light has radio and emits in microwave, infrared, visible, ultraviolet, X-ray, gamma rays. So there is a lot of information that comes through the light. And the visible, the light we can see with our eyes, it's a very small portion of it. What does this mean for astronomical objects? Well, it truly means that because the universe emits light at all wavelengths, we need telescopes at all wavelengths to really get a full picture of the complexity and the nature of these objects that surround us. In the case of the James Webb Space Telescope, we use infrared light. So what is infrared light? This is an example of two pictures of, we have meerkats and we have a crocodile, and this is how we see them with our own eyes. This is visible light. If we now put on our infrared goggles, this is how they look like. The meerkats, they are warm blood animals, so they are glowing, they're shining in the infrared, whereas the crocodile, being a colder blood animal, it's really more muted and more demure. So this is now giving the hint that infrared is an excellent way of measuring temperature, and everything, every object in the universe that has any temperature above zero emits in the infrared, which makes it an excellent tool to observe things like distant galaxies. So let's have another example. This is a firefighter, and the firefighter in this picture is surrounded by a cloud of smoke. So what would the firefighter see with infrared light? This is what it would see. It would have the ability of seeing through that cloud of dust and smoke and really see a person lying in the floor because it's glowing, it is really warm, and the temperature is making it very obvious. So this is again one of the powers of the infrared. You can see things, for instance, through dust, and you can also see the dust itself glowing in the dark. Let's have a practical example. This is a very beautiful galaxy, a spiral galaxy, as seen with the Hubble Space Telescope. This is visible, and we see all this glowing star formation. We see lines of dust, all those dark brownish lines. These are sites where dust is blocking the visible light. We see the nucleus. So it is a really, truly beautiful galaxy. But when you look at it in the infrared, this is how it looks like. It has now a more ghostly appearance. And if we go a bit back and forth, you will see that everything that was dark in this image is now glowing in the infrared. So all that dust that it is being the site of new stars being formed, it is now glowing in the dark. At the same time, we have all these cavities and sort of bubbles across the galaxy, and these are indications of the effect that the cycle of star formation has in galaxies, like clearing out all these spaces. So truly, infrared gives us a fresh take and a fresh view and a different type of information in this galaxy. JWST has four instruments on board, and they use different techniques to collect light and to provide information, but we're going to focus today on the two main ones, spectroscopy and imaging. So let's get started with imaging. JWST, as I said, does imaging. So cameras select light using filters. So in this example, we just have visible light with the usual colors. If we use a red filter, the red filter will absorb all colors except red, which means that we would get a red image of the object we're looking at. Of course, for JWST, the filter would select an infrared color, and we would be able to combine that color with other infrared colors. So it's truly a selection process that is very targeted to specific colors that we want to observe. What is a spectroscopy? JWST does spectroscopy, but what is a spectra? We saw before the rainbow created by Newton with a prism, and now we're seeing a rainbow here as well, but we also know that some materials, they do absorb light. They have that characteristic of absorbing portions of light. And the way this is represented here is with the vertical black lines. We also know that some materials emit light, and this is represented here as white vertical lines. So astronomers plot this absorption and emission lines as spectra, and this is what is represented here. All the dips are representing the absorption lines, and the peaks are representing the emission lines. And this is really a practical way of understanding the information we're looking at. And this is the way you do it in reality. So you have here this beautiful set of galaxies, and for two of them, we're taking a spectra, and you see there the light being dispersed. So in the dispersion of that light, we're finding out that actually they have oxygen and they have hydrogen. And not only that, but we're seeing that the hydrogen and oxygen are precisely at the same location. And this is an indication that we are looking at mirror images of the same object. We're going to talk about this particular object later on. But the point I want to bring here is that spectrum, it's equivalent to incredible science discovery. It really opens a new space because you can understand the composition. In this case, you know this object has oxygen and hydrogen. You can understand the temperature and the pressure and dynamics and how gas moves in galaxies and how stars evolve, etc., etc. So it's a wealth of information that we have access to. And in the case of JWST, about 75% of the time, it is doing a spectroscopy. So it's really a lot of information to unpack. Let's talk a little bit about cosmological redshift. What is redshift? So cosmological redshift is really the rate at which the universe is expanding. So we know the universe expands. So that means that faraway galaxies, they are moving even farther away from us. How do we interpret that with a spectra? This is a nearby star, and here we're just depicting a spectra with a set of absorption lines, again as vertical lines. If we look at a nearby galaxy and we observe the same lines, they will be slightly moved because the galaxy is farther away in a universe that is expanding. So the lines are moving slightly to the right, slightly to redder colors. If we look at a more distant galaxy, the same lines are more shifted. And finally, if you look at a truly distant galaxy, that in this case it's very small and it's supposed to be really far away, the same lines are truly moved to the right. And in this case, you see here there that the last line could, if the galaxy was farther away, would easily be out of the range. And this is how it looks in real life. So in this plot, it's a beautiful image where each horizontal line represents a spectra of one galaxy. We have more than 1,000 here. The lines on the bottom represent galaxies that are closer to us. The lines on top are galaxies that are farther away from us. And you see how that emission line, that bright line, for all of them, is just everything is moving to the right because everything is redshifted, because as you go up, objects are farther away. And again, for each of them, you would have, in this case, information of hydrogen and nitrogen and sulfur and oxygen. So again, a wealth of information to unpack on all the objects. So what is JWST in a nutshell? It's a large infrared optimized telescope that is located 1 million miles away from Earth in a very stable orbit, kind of very easy to maintain. It is protected by, it has a sun shield, as you can see in this depiction, and the function of the sun shield is to protect it from the radiation of the sun and the Earth. And the reason is because you don't want that heat to affect the measurements of the infrared. So you have to keep it really, really cold. It's also big. Why is it important? Here you have a comparison between the JWST and the HST mirror, so significantly larger. Why does that matter? Well, the size of a mirror in a telescope determines the level of detail and the sensitivity, or how faint objects, like how much fainter objects you can see, essentially. And this is an example. This is a region of the sky observed by the WISE telescope on the infrared. And this telescope had a primary mirror that measured about 40 centimeters. So there's not a lot of resolution, essentially. If you look at the same region of the sky with a Spitzer that had 80 centimeters, you see that you start to resolve more stars, you see fainter objects, and it really looks a lot better. With JWST and 6.5 meters mirror, this is what you see. Truly spectacular resolution. Things that are points or blurs on other images here are resolved like stars, and all that extended emission, all that sort of faint veiled structures you see, this is dust. This is dust that is glowing there and it's ready to be measured and understood. So that's why, in this case, being large matters. Let's begin talking a little bit about science with JWST. And typically, we talk about 4 pillars of science. The first one is the study of the early universe. And by that, I mean the study of the very first galaxies and stars that were forming the universe. And this is the main reason why this telescope came to be, because you need the infrared to observe that very, very, very far away objects that, with which the universe started. So we have the first galaxies that are formed, and these galaxies evolve in time. So the second pillar of science for JWST is the assembly of galaxies over time, which means how did those early galaxies evolve to become the galaxies we have today, including our own Milky Way. Galaxies are essentially the neighborhoods where stars live and evolve and happen to be. So the third pillar of science for JWST is the birth of stars and protoplanetary systems, because many stars end up forming planets around them. And finally, the study of planetary systems and the origin of life is the fourth pillar of creation. So what we're seeing here is that essentially with JWST, we can observe everything from the very early universe to our own solar system. So from Mars and out, everything is seen. And it's an observatory that is so flexible that essentially any size you can dream about in the infrared, you can attempt it, and you can do it with JWST. And we're going to start seeing some results starting from the beginning, the exploration of the early universe with Webb. This is an image I'm sure all of you have seen, and this was the first early release observation that was released, and it's a really beautiful picture of a cluster of galaxies that is in the center. Clusters of galaxies are really interesting objects because they act as natural telescopes. They are so incredibly massive that even the light from the objects that are behind, it's sort of distorted, that it bends around them. And that ends up, because it sort of goes around the cluster, it ends up creating mirror images of the objects behind. And not only they are mirror images, but they are also magnified. So to the power of Webb, you have to add the power of nature, and you end up magnifying all these little arcs you can see are galaxies that are behind the cluster, much farther away, and we can clearly see not only once, but 2, 3 times, depending on the configuration. Let's zoom in a little bit so you can enjoy a closer view of this. So all those arches are what I mean by magnification and gravitational lensing. And you see here how when you keep looking at this image, there are so many galaxies. I think there is no better way of describing it. There's just so many of them, and it's a very nice representation of what you get in an astronomical picture. All of these galaxies are located at different times and distances, but we see them in projection. There are thousands of them, and it's a truly fantastic image. And you also have stars. Stars are really easy to spot because they have the diffraction peaks. So what can we learn if we then take spectra of some of these galaxies? Well, as we talked about before, you can learn about their chemical composition. And in this case, we're focusing on hydrogen and oxygen. The galaxy on top is 11.3 billion years old. The second galaxy is 12.6 billion years old. And there you can see what we discussed before, how the lines shift because the galaxy is farther away. We're seeing the same hydrogen and oxygen lines. The third galaxy is even farther away, and the next galaxy it's a little bit farther away. Remember, the universe is about 3.8 billion years old. So are these the oldest galaxies JWST has seen? And the answer is no. The oldest one we've seen to date is this one. It's called JADES GS-Z140. And in this little zoom on the image on top, there are actually two galaxies. The one on top, the white one in projection, that is closer to us. The farthest away galaxy we've measured to date is the one in the bottom, the red one. And this galaxy existed about 300 million years after the Big Bang. So in a very, very young universe. If we pack the life of the universe in a single year, in a single calendar year, this galaxy existed at around January 7th. So it's really, really, really young. And it's young, but at the same time, it has had the time to have some chemical enrichment and have some sort of evolution. So certainly it is not the first galaxy that was created, but it's the oldest one we've seen to date. And that's a really exciting result. So let's have a look at how do we study galaxies over time and what happened to these galaxies. So one process that galaxies go over very frequently is the process of interaction and merging. This is an example of them. In this case, the galaxy to the left is not part of this group. It is closer to us, but the projection makes it look as if it was. This is a Stephan's quintet. And you see the galaxies to the right, how they are distorted, they have plumes, they have lots of structure, they are creating shock fronts that trigger star formation, and this is all part of a very common process of interaction and merging that all galaxies go through at some point. If we look at a different infrared color or colors, this is what we see. We see dust. We see sites of young star formation. And at the top galaxy, we see a point source in the center that is an AGN, an active galactic nucleus. Essentially, it's a black hole that is actively eating, if you want, material around and releasing lots of energy. If we then use spectroscopy to look at the gas around that black hole, we see that it has iron and argon and sulfur and neon. So again, lots of chemically rich materials, and we are able to understand what are they and what are they doing and how they move around that black hole. This is another example of a collection of galaxies to illustrate how JWST with its infrared powers allows us to see all these structures and to really put them in the context of how does star formation impact galaxies. So again, galaxies, there are many stars in galaxies. So stars live within galaxies. And how are they born and how do they die? This is a very nice Spitzer image of a gigantic cloud where many stars are being formed. This is a site of active star formation. And here at the center, this is Rho Ophiuchi. And this is how you can see it. This is how it looks like with JWST. Again, truly a spectacular image. This is a site of a star formation where about 50 stars, very similar in mass to our sun, are forming. The star at the center, slightly more massive, it's very young. It just sort of it's getting out of its cocoon of dust and material, and it's really getting out of starting its life essentially as a star. And it is illuminating all the material around. That's why you have that sort of yellow, beautiful cocoon of dust around it. If we have a little bit of a tour, all these red structures, these are hydrogen jets that are created by protostars. So stars, they do form in disks. And as you can see in the image next, this one that looks like a bat, pretty much. At the center of that, there is a star being formed. The stars form in a disk. And the disk, at the beginning, you don't see the star because the disk is just obscuring and there's a lot of material, but you see those jets, very powerful, illuminated, um, sort of going like that from the protostar, and in this case, it's a hydrogen jet. So again, the level of detail this image is providing, it is truly spectacular, and it really helps understanding how stars are born. We said here these are about 50 stars similar in mass to our sun. So what is the future of these stars? So stars like our sun, they die as planetary nebula. So at some point they become what we call a red giant. And in the attempt of maintaining its equilibrium, they start shedding the outer shells. And in that shedding, they enrich the environment around. So stars are the chemical factories, the factories where the chemical elements are produced. At the beginning of the universe, after the Big Bang, everything was mostly hydrogen and helium. All the rest of the elements are composed in stars. And when the stars die and when they shed layers and they sort of enrich the elements and they create inside them, inside their nuclear power station, they create new materials. When stars are a lot more massive than our sun, let's say 10, 20 solar masses, they explode as supernova. And in that explosion, again, they create heavier materials and they shock the environment. So that means that potential clouds of star or interstellar medium, it gets shocked and compressed and can even trigger future star formation. But also the elements and all the materials from the star, it enriches the environment around, and it's the resource that you have to create new generations of stars. Finally, this is a very beautiful example and very recent. This is a cluster in the Small Magellanic Cloud. It is a nearby galaxy, really small and really close. And the special thing about this image is that the team that produced it, they have found candidates of brown dwarfs for the first time outside our galaxy. So brown dwarfs are somehow some objects that are between planets and stars. They are really not planets because they don't orbit around the stars, they are free floating, but they are also not stars because they don't have enough mass and enough power, if you want, to start nuclear reactions. They don't burn hydrogen in their core. So it's like something in between. And in this image, for the first time, they have detected candidates of brown dwarfs outside our galaxy, which is truly a feat. And it's really thanks to the power of JWST, the power of resolution and sensitivity. So stars often form planets around, and JWST also explores that in a lot of detail. This is another example of a region where stars are being formed. And you see in the zooming at the bottom right, that's a star with a protoplanetary disk. So that means that around the star, there are materials and enough potentially planets can form in there. And the reason why it is not like a nice disk, it looks like misshaped almost. That is because all the stars radiating from the top part essentially are creating winds and the radiation, and that is really impacting the star and the forming the disk. But this is a place of potential planetary formation. So again, why are we interested in that? Why are we characterizing, in this case, water abundance? Well, the truth is that planets form in disks around the stars. So the more we understand the conditions that allow the formation of planets, the better we can understand how planets are formed and how our solar system was formed, etc., etc. So in this case, this is a study that compares compact disks versus not so compact disks and warm water and cool water. And it's all about what materials are available to create planets and how they move within the disk and how they sort of how is it possible from a disk to end up having a planetary system? And this is again where spectroscopy gives a really incredible, rich set of information for understanding all of this. So once a planet is formed, it orbits around a star. And this illustration depicts a technique called transiting exoplanets. So you see, when the planet goes in front of the star, the light of the star is dimmed, and it's also filtered through the atmosphere of the planet. And that's a tool to learn about the composition of planet atmospheres. So JWST has detected many molecules in giant planets, and in the following, we're going to talk about two big type of families of planets, if you want: giant gas planets and rocky exoplanets and rocky exoplanets. So this is an example of giant gas planets atmospheres, and as I was saying, JWST has detected many, many molecules of them, many of them for the first time. So it's really producing a catalog of chemical abundances and chemical composition and atmospheric compositions for different exoplanets. It's also has been also able to measure day and night variations in temperature in an exoplanet, which is truly a difficult measurement. It really tells us about how dynamic the atmosphere in the exoplanet is, because you can measure variations from day to night. So truly, yeah, it's amazing. And finally, JWST has also measured an atmosphere in a rocky exoplanet, which again, it's a very hard measurement to do because planets are very small. The amount of light that filters through the atmosphere is really tiny, but with enough stability as JWST has, and with enough sensitivity and control of the data, you can actually do this measurement. So this was, in my opinion, one of the excellent recent discoveries of JWST in exoplanets. Finally, JWST explores our solar system. And really, you could think, well, solar system, very bright, very big, very close. Why do you need such a big telescope? And the answer is in this beautiful Jupiter image, because the detail, this is an aurora, the detail with which you can study the closest planets we have to us, it is unheard of in the infrared. So here you have the atmosphere, you see the clouds and turbulences, and you see how beautiful the famous big red spot of Jupiter is. And actually, when you look at it with other JWST instruments, the recent results show that they have the great red spot has a cold heart. So it is cold. It also has patchy clouds. So it's really opening the window to fully understanding, or let's say, improving all of our understanding of the dynamic of this very close solar system planet. This is another example. In this case, this is Uranus with all its satellites, or most of its satellites. And if we zoom in, again, you can see with the detail with which you can measure it, but not only that, you see so many galaxies in the background. And again, we go back to the projection effect and the detail with which you can observe it. So in this case, not only you're seeing a very close by solar system planet with its satellite and rings, etc., but you also see galaxies in the background. And if we zoom in into Uranus, we can see clouds in the atmosphere, we can see the polar cap, and we can see beautifully detailed all those rings. I mean, never seen before this detail in the infrared. Finally, JWST has very recently studied centaurs, and centaurs are objects that orbit around the sun, and they are placed between Jupiter and Neptune. And these objects are really, you can think of them as leftovers of the early solar system materials that were available for forming planets. And they are very cold, so they are sort of preserving that very young, very early stages of the solar system. And in this case, the team has seen that gas is sweeping out from this center in the form of jets. So it's allowing to study things like CO and CO2, and really understanding what are the materials and the products that were available when the solar system was in its infancy. So I'm going to leave you with this very nice video based on real data. This galaxy is called the penguin and the egg for obvious reasons. This was our second year anniversary image. And it's just a very nice overview and detailed exposure of emerging galaxy that again gives you a sense of the incredible. I feel we are all incredibly lucky to be able to have this beautiful telescope providing this incredible data and images and really enhancing our knowledge of the universe and charming all of us with all the data. So my time is up, and I just wanted to thank you for your attention, and hopefully we'll talk about JWST and its science very soon. Thank you.
Hi, my name is Eric Kosh. I'm a postdoctoral researcher at the Harvard and Smithsonian Center for Astrophysics. It's my pleasure to present to you some of the first work on nearby galaxies in JWST's first 2 years. I'm presenting this on behalf of a much larger collaboration of about 130 people that make up the Physics at High Angular Resolution in Nearby Galaxies Survey, or PHANGS. And so we were lucky enough to have some of the first pictures of nearby galaxies that JWST ever took. And this is one of them, perhaps the one that's become the most famous so far from our survey. This is the galaxy NGC 628. It's almost completely face on from our point of view from here within the Milky Way. And what we can see is this beautiful grand design spiral and the immense amount of structure that JWST identifies by tracing the emission of this galaxy in the mid and near infrared. Now we're going to come back to this galaxy in a few places, but just note that this complex structure isn't just found in this one galaxy. We actually have a larger set of 19. And this is what we were observing in the first year with JWST. And just to give you a quick sense of just the amount of structure and diversity amongst these galaxies, we're just going to zoom in to a handful of them. What you see in the blue light is the near infrared. It's mostly telling us where the stars are located. And the orange is telling us about the emission from dust that's mixed together with interstellar gas. And what you can see within these different galaxies is the different structures that they have. Some have spiral arms, some have these sort of nuclear rings around their centers, and some have these bars that trace gas flowing into the center. There's so much structure within these galaxies. And this really begs the question, what are we actually looking at? And in particular, what I'm going to be talking about here is the vast range of bubble-like structures. So the absence of the gas, and what we're tracing is sort of the shells using JWST. And so what are these from, and what can we learn from them? So let's go back to this picture of NGC 628. So to understand how such bubbles form, and why we're seeing so many of them, we need to actually zoom in into a single star-forming region. And so from here, this view of the entire galaxy, we're going to zoom down into much smaller scales, sort of 100 light years or so. And now we're transitioning so that this full screen would be about 100 light years, the same size as that circle in the previous slide. And what I'm going to show here is a numerical simulation of an individual star-forming region, what we call as a cloud. Now this is zoomed up by, this is sped up by quite a bit. We're essentially watching the evolution of this cloud as it forms stars over several million years. And what we started out with is this collection of cold gas. The motions in the gas are quick enough that we get supersonic shocks everywhere. And as a result, it forms these filamentary-like structures that you can see here as we zoom around. Within these filaments, some of the regions can then gravitationally collapse, allowing gravity to take over in small portions. And this is ultimately what leads to the formation of stars. Now, if this process was so simple and just included turbulence and gravity, the story wouldn't be nearly as exciting as it is in reality. What we need to account for is the fact that once those stars turn on, they inject a significant amount of energy back into their surrounding areas. And they do this by different mechanisms. One of the first that turns on are these protostellar jets that you can see starting to appear here in the simulation. So even though these are coming from just a single star or stellar system, they affect a massive area surrounding them, influencing the ongoing star formation in the rest of the cloud. After a while, stellar winds start to contribute. That's leading to some of the bubble-like structures that you're seeing here towards the top of the screen. All while turbulence is continuing to create these filaments and gravity is continuing to form stars. And what we're watching here is the assembly of a larger stellar cluster resulting from this cloud as a whole. Over time, significantly larger cavities begin to be formed around this cluster. And this is the birth of these much larger holes and bubbles that we saw previously in the galaxy NGC 628. Now, one of the most important parts is this is actually how we think star formation turns off. Over the lifetime of one of these clouds, only about 1% of the gas is turned into stars. The rest is held up. It's not able to gravitationally collapse. And we think that it's mostly the energy from these stars after they form that shuts off or stops the remaining gas from forming stars. And it does this by heating the gas and starting to blow these bubbles and dispersing the cloud as a whole. So since this cluster has been around for a while, we're now starting to see these larger cavities that you could imagine starting to be identified in these other nearby galaxies. But there's one more trick up our sleeve, and that's in these massive stars. The brightest ones that give off the most amount of energy, despite having the most fuel, they burn through it very quickly. And as a result, their lifetimes are short, and so they die in supernovae, and that's the shock that you saw go through the gas, while they're still in the cloud that they formed from. So all of this detail is happening within just a single region of these nearby galaxies. So one of the most interesting things about studying these galaxies is we can build up massive samples and look at how the evolution of these bubbles and star formation exist. And one of the other interesting points is, in particular, new work about our own solar neighborhood around the sun. And so I'm going to take this box and I'm going to put it now on top of a bird's eye view that we get if we zoomed out above the Milky Way from our position at the sun. This is a diagram showing a combination of data and models. It's what the gas would look like in our surrounding neighborhood as traced in 3 dimensions. And this is brand new work that's been enabled by the Gaia satellite, which gives us distances and proper motions of the nearest stars. So this blue region here is a model for what we think our own local bubble is, and the sun just happens to be passing through, and right now we're close to the middle. So now I'm going to switch from a top-down view to an artist's rendition of what this bubble looks like from the side. Now the sun is that thing in the middle. It is not to scale. The sun's much smaller and not nearly that bright. And the things that you see around the edge are all of the nearest star-forming regions to the sun. And in work led a couple years ago by my colleague, Catherine Zucker, she showed that we can actually trace the history of this bubble as it began from a set of supernovae and expanded over the last 14 million years. And as it expanded, it drew up gas and dust leading to the formation of all of the nearest star-forming regions to us around the sun. And this is enabled again by this Gaia satellite, where we can trace back in time where young stars were when they initially formed. This is potentially very interesting because it suggests that not only does stellar feedback turn off star formation in individual clouds, but can also seed the location of the next generation of stars. Now, unfortunately, we can only get this kind of detail within our own solar neighborhood. So while we have a very good idea of this process from our own local bubble, it's hard to generalize to a larger sample with the data we currently have in hand. So let's zoom out again and see how this more broadly fits into our view that we get now with JWST and these nearby galaxies. So now that we've pointed out the bubbles, you're probably seeing hundreds of these. And just to give you an idea of why JWST is so revolutionary in this area, I want to take a step back and look at the data in combination with what we had access to before. This is the same image of the galaxy. We're just looking at a single filter, so it's shown in grayscale instead. This is the center of NGC 628, and I'm going to bring up in comparison the same wavelength as traced by the last generation of infrared telescopes, the Spitzer Space Telescope. And it becomes immediately obvious the limitations that we previously had using only the Spitzer data. JWST's resolution and sensitivity is so high that we can now pinpoint these individual bubbles in a way that we just simply could not with previous data. And the location of these bubbles was really just one of the first surprises that we had as we started to get these pictures. So this particular image of NGC 628 was one of the first galaxies that, or nearby galaxies that JWST observed. And initially, I was sharing these initial results at a conference with other researchers studying the interstellar medium and star formation. And it actually took people quite a while to believe that this was a real image and not a simulation. We're used to seeing these kinds of structures in this sort of infinite detail within numerical simulations of galaxies, but this is really our first time of seeing that structure in reality in a nearby galaxy. So we have all of these bubbles. We want to look at their properties and understand them as a whole, as a population, and better understand how they both stop star formation within individual regions, but could also potentially seed it around the edges of these bubbles as they grow. And so the initial work on this was led by my colleague Elizabeth Watkins as part of the rest of the FANGS team. And she identified nearly 1,800 bubbles within this one galaxy. Now, this is the same image that I was showing before. It's now just reoriented along the celestial coordinates. That's why it looks like it's been placed at a different angle. So this would be sort of positioning it as you would see it on the sky. And from this large sample of bubbles, in particular, we found that these larger ones have these series of nested bubbles along their edges. And qualitatively, that's a similar picture to what we're seeing within our view from the local bubble. That newer star formation is triggered at the edges and it starts to form its own set of bubbles. And we're just seeing these nested sets of bubbles and holes at different stages of their evolutionary path. Now, this was a colossal undertaking to just identify these first set, but of course, we don't just have one galaxy, we actually have 19 with all of their diverse structures. And even over the past year, we've been expanding this sample with another program that's going to add, or is about to add, another 70 more. So we have almost 90 galaxies. If we're finding roughly 2,000 or so bubbles in each of these galaxies, this means that we're expecting that the data that we're already have in hand or are about to have could allow us to identify well over 100,000 of these feedback-driven bubbles. And such a large sample is critical because, again, we're looking at a several mega-year process, several million years, and we only get this one snapshot. So we need a huge sample to understand how these bubbles vary and are connected to previous generations of star formation by just looking at a massive sample. We need to build up sufficient population statistics to better understand their age and evolution. And the way that we're going to be doing this is via a citizen science project called Bubble Zoo. This is in collaboration, again, with FANGS, but in particular with Liz Watkins and Eric Rosalowski and myself. This will be a new project appearing soon on the Zooniverse platform. And I'm showing you just an example of what one of our small cutouts will look like, where you can help us explore these very intricate data sets and identify all of these bubbles. This is essential for us to better understand how this is connected to star formation and eventually how galaxies evolve through many different cycles or many different evolutionary cycles of this star formation process. This sample will be well over 1,000 times larger than anything that we've had before. And so it's really critical to be able to measure their properties so that we can learn a number of unanswered questions about this star formation process. And so with that, I'm just going to leave you with my conclusions and thank you for your time. Again, this is about work on behalf of the FANGS collaboration, in particular, the early work done by Liz Watkins, who is also attending this workshop. And if you're interested in her work, you should absolutely go and ask her more questions about it. I can be reached via email, or you can find more information about my research on my website. And I'd like to thank my colleagues at the CFA, Catherine Sucker and Theo O'Neill, who helped provide some of the slides for this presentation. So in summary, JWST is showing us that nearby galaxies are ubiquitously filled with these bubbles. Those bubbles can be similar to what we are in within our own solar neighborhood in the current location of the sun. And we'll be launching this Bubble Zoo project to help us identify the largest sample of these bubbles that have ever been traced before and use that to better understand the star formation process. Thank you.
Hello, my name is Jan Scholz. I'm from Cambridge University, and today I would like to talk to you about the look into the first galaxies and black holes with the JWST and specifically with the JADES survey. And I just would like to say this is on behalf of JADES survey. I'm just a small cog in it. So, at the beginning, we had the Big Bang, that's sort of 13.7 billion years ago. Then we had something called the recombination, and then eventually dark ages, where the dark ages were sort of before the first stars and before any galaxies. And then slowly you had the first stars in sort of within the first 50 million years after the Big Bang, and eventually first galaxies. And these first galaxies, that's what we call the cosmic noon. The cosmic morning, which is when actually the first galaxy and the first stars and actually started illuminating the entire universe. And before, we mostly use ground-based spectroscopy or alternatively ALMA array in order to study these. But if you really want to push into looking at these very distant galaxies and the first stars, you really need JWST for this because it's observing in near infrared light, which I'm going to talk about later. And it's incredibly important to stress that JWST is currently the largest telescope in space. There is so far nothing bigger that can rival it, even close. And if you actually look into the comparison of this, JWST with its hexagonal mirror has a size of roughly 6.5 meters, but HST, which is something that it's replacing JWST, the successor to Hubble Space Telescope. That one was roughly 2.4 meter. So more than the HST was already the main mirror was already larger than a person at 1.8 meters. So this is a huge increase in size. And because of this, we get much better resolution, so the sharpness of the images, but also much bigger collecting area. Now, this larger collecting area is allowing us to look into more distant stars and more distant galaxies. And this is this incredibly thing about universe is that light is essentially a time machine, because light has a limited speed. So the more distant things you look at, the more you look into the past. So, for example, the sun is roughly 8 minutes away from us at the speed of light, which means that we always look at sun roughly 8 minutes ago. If you look at Mars, that's roughly a few hours ago. If you want to look at sort of the center of our galaxy, that's a couple thousand years ago. Closest galaxies can be even a couple million years ago. And if you detect the most distant galaxies and their first stars, you will essentially look at the universe as it was more than 13 billion years ago, and that is the true power of these large telescopes and looking into distant galaxies. So the first launch was on 23rd of December 2020. 2021. That was a very stressful Christmas day for everybody involved, but luckily things went absolutely perfect. The launch trajectory was absolutely perfect, which has consequences that I'm going to show later on. Very good consequences. And then the telescope was separated from the rocket, and we could actually start unfolding the telescope. So first they unfolded the solar array, then the communications antenna, so that we could actually communicate with the telescope, and then came the sun shield. So we need to keep the telescope as cold as possible, and because of this, there's this large sun shield that actually blocks any light coming from moon or Earth or even the sun, in order to keep it nice and cold. So that was extended. This was something that it looks relatively small, but actually the sun shield is the size of a tennis court. Then you start cooling. You start actually assembling the telescope itself. The mirrors started unfolding until you have a fully functioning telescope. And then there was this spectacular process of calibrating all of the instruments and doing the first images, where the people who, over the 6 months, who were involved, have done a spectacular job to preparing the telescope for science operations. So, because the telescope is optimizing for detecting infrared and detecting infrared, it's actually gold-plated. The mirror is from gold. It's a beryllium mirror coated with gold. Usually on the ground for optical light, we use aluminum, but it's very bad for reflecting infrared light. So there we use gold. The sun shield is essentially a multi-layer sun shield. So on the side of the sun shield, it's roughly 50 degrees Celsius, where the sun is shining, and on the other side, in the shaded area, it's roughly minus 230 degrees Celsius. So you have more than 280 degrees Celsius difference across the sun shield in order to make the telescope as cool as possible, which is fascinating on its own. And the image quality improvement is beyond unbelievable. When you look at the WISE and the Spitzer, which are the previous infrared telescopes, and you compare it to the current one, you can just see this beautiful nebulae and the gas clouds compared to just little blobs and blobology that you saw in the previous telescopes, which I would like to point out, they were still amazing, with older technology. This is the leap in technology we are talking about JWST, and it's not just sharpness in images. It's also in terms of sensitivity. The sensitivity improvement is several orders of magnitude compared to the previous observatories. And for some wavelength range, this is the same as going from Galileo Galilei's telescope to a very large telescope, modern astronomical facility. It's the same leap. It's spectacular. And this is amazing advance in sensitivity and resolution allows us to look to sort of investigate the first galaxies. So this is something as a pre-JWST look. We thought that as you go further and further to younger and younger universe, that the galaxies should start behaving more chaotic. Because it takes a while to develop a nicely rotating disky galaxy. So you can see, so on the left, very nice spiral, and then as you go further and further, kind of you see these blobs and this sort of messy systems. But actually, when we look into the first images, and you can look at this visually, you don't have to do much of a scientific analysis. You just get these beautiful spirals, these beautiful evolved galaxies. This is one of the deepest observations currently with JWST. This is from the JADES survey, and every single point that you see in that image is a galaxy, and they are beautiful. They are spectacular. When you even compare it to just sort of ground-based, right, where before there was just sort of 4 or 5 little galaxies in a small region where we saw it, and now when we look at it with JWST, suddenly we realize that this sort of a little tiny cluster or overdensity of galaxies that wasn't even everything within the overdensity. There are tons of more galaxies there. That's performing this little they are performing this little dance. There are some where we saw them as like little red blobs, and now we see them as these beautiful spiral galaxies. On some of them, we just didn't see them in the first place, right? So they are just completely new discoveries for us. The same thing goes with Hubble's. When you compare Hubble Space Telescope and JWST, what before was sort of a mess, now is a beautiful spiral galaxy as well. So that is spectacular. And then finally, when you look into, you actually start to see that there are a lot of sort of evolved major spiral galaxies seen by JWST, and we see way more of them and way earlier. But the thing is that the strength of JWST is not just looking at images, it has a spectrograph. So with spectrograph, you can look at it that, first of all, you can start with simple 3-color image, your blue, green, and red. You can sort of look at their brightness, you will see something. And then you'll kind of start looking into filling the differences between the gaps between the different colors. You will start increasing them with more and more filters, and you will get more and more colors. However, at some point you realize that's actually really an efficient way of doing this with just more and more filters, because you want to keep dissecting the light, because every single time you dissect the light to a little bit smaller color, it actually gives you more information. So you can start using, for example, prisms, where you shine light through a glass prism, and you get the rainbow, and in the rainbow you can have tons of information. Or alternatively, you can use something called a grating, which is sort of a different prism. And essentially what you get is this sort of incredibly finely you get the rainbow, the incredibly finely dissected sort of colors. And that's incredibly important, because all of these peaks that you see in that's actually a transition from emission line from some sort of element, whether it's oxygen, hydrogen, neon, carbon, or whatever. And actually they can tell you tons about the sort of chemical composition of the galaxies and of the stellar population, and etc. And one other thing is that we need to start looking at infrared, because we are looking at galaxies so far away that the universe has actually expanded a significant amount between then and now, which means that also the light that they emitted, for example, in UV or optical wavelengths, has been essentially stretched in the due to cosmological expansion, all the way to the longer and longer wavelengths until they ended up in infrared, into much longer wavelengths. And this is what we call the cosmological redshift. This is something that's how we measure the distances and distances of galaxies and also their ages. And I would just like to give you two examples of the most distant galaxies or black holes that we discovered with JADES. So one of them is something called the GSZ14, and you can see sort of the field how we discover it. And among the field, we also you can also see a sort of the image. It's actually right next to a foreground galaxy. There's this sort of a blue part in that little span, and it's only the red one, the smaller one, the red one, that's actually our galaxy. This one is at redshift 14, and the reason why we know it is because we got a spectrum from it. So we dissected all the different colors, and within that we actually found that there's a sort of a rising continuum until there's a very sharp break, which we call the Lyman alpha break. And it's essentially, the break is caused by neutral hydrogen that actually absorbs all of the light that is bluer, shorter wavelength or bluer than the Lyman alpha break. And that is supposed to be at exactly one wavelength. It's 1215 angstroms, or 0.12 microns. So if we know where we actually detected in the spectrum and where it was supposed to be, we can calculate the redshift, sort of how much it has shifted, how much the universe has expanded, and based on that we know the distance and we also know the age. So this is something that is less than 300 million years, roughly 280 million years after the Big Bang, which is sort of, we're talking about 13.4 billion years ago. Now, GSZ14 it's quite massive, actually. It's 830 million times the mass of the sun, and it's roughly 820 light years ahead. But it's still, when you look at it compared to our Milky Way, which is over 1 trillion times the mass of the sun and 100 light years across, is that this thing is just an embryo of a galaxy that one day is going to become our galaxy. We see the embryos of our own galaxy at this point. This galaxy will have to grow by almost a factor of 1,000 in size, and then also more than a factor of 1,000, probably more, in mass before we actually reaches what we call a galaxy today. The other one that I would like to talk to you about is GNZ11. So what's spectacular about it is that this is the most distant galaxy detected and observed by Hubble. And it was always a puzzle to the astronomers because it was incredibly bright compared to what we would expect. So this is a JWST image of it. It's sort of the orange blob in the middle. If you wonder what is that red galaxy in the top left, that's just a foreground galaxy. It's significantly closer to us. It just happens to be there by chance. And I just wanted to show you this HST spectrum of GNZ11, which is something that was done by Pascal Oesch with incredibly effort by HST to get this spectrum, and therefore they also saw the very sharp drop, the very sharp break, and they realized that this is roughly a redshift 11, hence GNZ11. And the JADES collaboration could not wait to actually see the spectrum. And we got a spectrum of it. And this is what we got with JWST. So completely different sort of quality. Look at the beautiful sharp break. Look at all of those peaks, which are actually all of the emission lines from nitrogen, carbon, neon, oxygen, that just show you. And actually, when you do a deep dive into all of these emission lines, what you actually find out is that this thing hosts a supermassive black hole, a very active supermassive black hole. And the material that's infalling into the supermassive black hole is shining a huge amount of harsh radiation that's causing some of this emission line, and also it's causing this incredible brightness that we before didn't really expect. Also, it has a very complex what we call morphology or shape. So it has a sort of a point source in the middle with a disky galaxy underneath, and then there's this haze, this sort of like an extended structure that we don't really know what it is. But when you look in even in further, you actually realize that there are tons and tons of galaxies around. So on the left, you see an image of couple of, in the blue, of couple of sort of like other galaxies that we saw around it. The orange are just foregrounds, contaminants. But when you look at the image on the right, and then you see little numbers across all of on the image, and you actually what you find out is that there are just tons and tons of galaxies all around it, and the same rough what we suspect is the same distance as GNZ11, which would indicate that it's essentially in something called a protocluster, or it's like a very early density, the over density that will one day become a cluster of galaxies. And this is something that has been happening 400 million years after the Big Bang. So there's this incredibly fast growth of structure in the universe. So in summary, within the first 2 years of JWST operations, we already broke the record for the most distant galaxy twice. There's one called GSZ13. I didn't even talk about that one. Then we have GSZ14. We the JWST discovered the most distant black hole, and we find that just galaxies evolved way faster than we thought before the launch of JWST. And we see evolved galaxies with evolved black holes less than 500, 600 million years after the Big Bang. And that's just incredible. Nobody thought that the universe was going to evolve so quickly. Yeah, I cannot wait to what's going to happen for the next 20 years of scientific operations of JWST. Thank you very much, and let me know if you have any questions.